There is no single doorway through which life must enter the universe. For a long time, the search seemed simpler than that. Find a rocky planet. Place it at the right distance from a steady star. Look for temperatures that might allow liquid water to remain on the surface. That was the first map, and it was a useful one. But every useful map leaves something beyond its edge. The deeper astronomers look, the more habitability begins to resemble a set of overlapping conditions rather than a fixed location. A world may circle within the traditional habitable zone and still be dry, airless, or wrapped in an atmosphere too dense for its surface to remain temperate. Another world may orbit far outside that zone, sealed beneath ice, yet keep an ocean warm through the pull of gravity and the movement of its own interior. So the question is no longer only where life could exist. It is how a world holds energy, how it moves matter, how long it preserves chemical opportunity, and whether those conditions remain stable long enough for simple chemistry to become something that can copy itself, adapt, and continue. Beyond Earth, there are many possible settings for that beginning. Some may resemble the early oceans of our own planet, with sunlight crossing a young atmosphere and reaching water filled with minerals and carbon-bearing molecules. Some may lie in the dark beneath frozen crusts, where liquid water meets warm rock and chemical gradients replace sunlight as the source of usable energy. Some may exist under skies that never change, on planets locked with one face toward a small red star and the other turned permanently away. Each setting changes the problem. Water matters, but water alone is not enough. Carbon is versatile, but carbon alone does not organize itself into life. A planet may contain the right elements and still lack the cycles that bring them together. It may possess an ocean but no lasting source of energy. It may begin with a mild climate and lose its atmosphere before biology has time to take hold. It may remain stable for billions of years and yet never cross the unknown boundary between complex chemistry and the first living system. That boundary is still hidden from us. Earth crossed it very early in its history, but the record of the crossing has been altered by geology, buried by time, and rewritten by life itself. We know that biology emerged. We do not yet know how likely that emergence was. One world cannot tell us whether life begins easily whenever conditions permit, or whether our planet followed a path so improbable that most other suitable worlds remain empty. This is why the search has widened. Astronomers now study planets around distant stars, but they also study moons, atmospheres, stellar radiation, planetary interiors, magnetic fields, ocean chemistry, and the long thermal histories of worlds. The search for life has become a search for environments that can keep possibilities open. Tonight, the journey moves through those environments, one layer at a time, not toward a list of places that are certainly alive, because no such list exists. Instead, toward the worlds where life might begin, the forces that could sustain it, and the limits of what our instruments can presently know. Somewhere between starlight and stone, between water and time, the universe may be repeating a process that happened here once. We are only beginning to learn where to look. The first clue is water, though even water becomes more complicated when examined closely. Every organism known on Earth depends on liquid water. Inside a cell, water is not simply a background substance. It is the medium in which molecules meet, separate, fold, exchange atoms, and release energy. Nutrients can dissolve within it. Waste can move away. Delicate chemical structures can rearrange without becoming locked in place. Water is useful because its molecules carry an uneven electrical charge. One side is slightly positive, the other slightly negative. This allows water to surround ions and interact with many different compounds, keeping them available for chemistry. It can carry minerals from rock, transport salts through an ocean, and help larger molecules assemble into structures that would be difficult to form in a dry environment. It also changes temperature reluctantly. A large body of water can absorb considerable heat without warming too quickly, then release that heat without cooling all at once. Oceans moderate the climate of Earth in this way. On a smaller scale, water helps protect the chemical machinery inside living cells from abrupt changes. And when water freezes, the solid form floats. This familiar detail has consequences. Ice can spread across the top of a lake or ocean, while leaving liquid water below. The frozen layer becomes insulation, slowing the loss of heat into the air or space above it. On Earth, aquatic ecosystems can survive beneath winter ice. On a distant moon, the same property may allow an ocean to remain liquid beneath a crust that has been frozen for billions of years. Yet, the presence of water does not reveal whether a place is alive. Water exists in comets, interstellar clouds, planetary atmospheres, frozen moons, and shadowed craters. It appears in regions that are far too cold, too dry, or too chemically inactive to support known biology. Even liquid water can occupy an environment where temperatures, pressure, acidity, radiation, or salinity place it beyond the limits of terrestrial life. What matters is usable water within a larger system. The system also needs chemistry. Life on Earth is built mainly from carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are not confined to our planet. They were produced through cosmic processes that began long before the solar system formed, then gathered into dust grains, asteroids, comets, planets, and moons. Carbon is especially valuable because one carbon atom can bond with several others at once. It can form chains, rings, branches, and layered structures. These frameworks can remain stable while still allowing change. They provide the architecture for proteins, sugars, fats, genetic molecules, and the countless smaller compounds that cells use. Organic molecules, however, are not proof of life. They can form without biology. They have been found in meteorites and in clouds between the stars. Carbon chemistry begins naturally wherever suitable atoms, energy, and environmental conditions come together. The universe can prepare ingredients without assembling them into organisms. For life to begin, chemistry must become organized. Some molecules must gather rather than remain diluted. Reactions must occur in sequences rather than at random. Useful products must be retained long enough to participate in later steps. A boundary may be needed to separate one chemical environment from another, much as a cell membrane separates the interior of a living cell from the world around it. This is one reason scientists study shorelines, mineral surfaces, pores in rock, sheets of ice, and hydrothermal vents. Each can create small compartments. Each can concentrate molecules that would otherwise disperse. Each can bring different chemical conditions close together. At a hydrothermal vent, warm, mineral-rich water rises from the seafloor and meets cold ocean water. The boundary between them contains gradients in temperature, acidity, and chemical composition. Those differences represent stored energy. Life needs such differences. A perfectly uniform environment may contain water and carbon, yet offer little that chemistry can use. Biological activity depends on movement from one state toward another. On Earth, plants use the difference between energetic sunlight and lower energy chemical products. Many microbes use differences between oxidized and reduced minerals. Other organisms survive through reactions involving hydrogen, sulfur, iron, methane, or carbon dioxide. The source does not have to be sunlight. This widening of the idea is important. Sunlight powers most life visible on Earth's surface, but it is not the only available energy source. Far below the ocean, entire microbial communities live without direct contact with the sky. They use chemical energy released when water reacts with hot rock, or when compounds from Earth's interior mix with seawater. A buried ocean on another world could operate in a similar way. It might remain dark from the moment it formed. It might never receive a sunrise. Yet, if liquid water reaches a rocky seafloor, and if the interior continues to supply heat and reactive chemicals, the ocean could contain energy that living systems might learn to use. Whether life could first arise under those conditions remains uncertain. An environment that can sustain life is not necessarily an environment that can create it. Existing organisms arrive with membranes, enzymes, genetic information, and intricate systems for repairing damage. The first living chemistry had none of these advantages. It had to build complexity before complexity existed. That may require changing conditions rather than perfect stability. Wet and dry cycles can concentrate molecules and encourage new bonds. Freezing can exclude salts and organics from growing ice crystals, pressing them into smaller pockets of liquid. Mineral surfaces can hold molecules near one another. Fluctuations in heat or acidity can drive reactions forward, then preserve what has formed. The birthplace of life may therefore have been restless on a small scale, while remaining stable on a large one. A world must preserve opportunity long enough for many chemical experiments to unfold. It must continue supplying energy without erasing every fragile structure that appears. It must allow molecules to gather, react, separate, and gather again. The useful conditions may not need to exist everywhere. A single shoreline, vent field, underground fracture, or pocket beneath ice could be enough. This changes how distant worlds are judged. A planet seen through a telescope is usually reduced to a few measurable properties: its size, mass, orbit, temperature, and perhaps parts of its atmosphere. But life would begin locally. It would begin in a particular pool, mineral pore, ocean current, or hidden boundary where conditions differ from the planetary average. From light years away, that small environment would disappear into a single point of light. The planet might appear too cold, while warmth survives below its surface. It might appear too dry, while water moves through deep rock. It might possess a harsh atmosphere above protected oceans or underground chambers. Habitability can belong to an entire world, but it can also survive in a narrow refuge that no distant instrument can yet resolve. Water opens the possibility. Chemistry supplies the material. Energy keeps reactions moving. And time allows the smallest useful changes to accumulate until a place that was only active becomes something more difficult to name. There is a second boundary around every possible birthplace of life, one that cannot be seen on the surface of the world itself. It is set by the star. A star determines how much energy reaches a planet. But that simple statement contains several different questions. How bright is the star? What colors of light does it produce? How steadily does it shine? How often does it erupt? And how will all of those qualities change over the billions of years during which life may need to begin and develop? The familiar idea of a habitable zone begins with distance. Close to a star, a planet receives more energy. Farther away, it receives less. Somewhere between those extremes, surface temperatures may allow liquid water to persist, provided the planet also has a suitable atmosphere. That last condition matters. The habitable zone is not a guarantee written into space. It is a range of possibilities calculated from models. A planet inside it can still be frozen, overheated, or dry. A planet beyond it may keep liquid water beneath ice or under an atmosphere rich in heat-trapping gases. The zone tells astronomers where surface water might be possible. It does not tell them what is actually there. Even the edges of the zone are not fixed. A planet with a bright cloud layer may reflect much of its star's energy and remain cooler than expected. A darker planet may absorb more light. A dense atmosphere can move heat from one hemisphere to another. Greenhouse gases can keep water liquid farther from a star, while too much of the same effect can push a world toward conditions where surface oceans cannot survive. The orbit adds another layer. A nearly circular path provides a fairly regular supply of starlight. A strongly elliptical orbit carries a planet through larger seasonal changes, sometimes approaching its star and sometimes moving much farther away. Oceans and atmospheres may smooth those changes, but only if they are deep or dense enough to store and redistribute heat. So a planet does not simply occupy a habitable zone. It enters into a long relationship with its star, its atmosphere, its orbit, and its own ability to respond. Our Sun offers one version of that relationship. It is a middle-aged, yellow-white star that has remained stable enough for Earth's climate and oceans to persist through most of the planet's history. Stable does not mean unchanging. The young Sun was dimmer than it is now, and it has gradually brightened as conditions in its core have evolved. Earth has remained habitable, partly because the planet itself has changed with it through atmospheric shifts, weathering, ocean circulation, and the long recycling of carbon. The Sun will not remain suitable forever. As it continues to brighten, the inner edge of the solar system's habitable region will slowly move outward. Far in the future, Earth's surface will become too warm for its oceans to remain. Habitability is therefore not only a question of where a planet is, it is also a question of when. This moving window appears around every ordinary star. Hotter stars shine more intensely and place their habitable zones farther away. They also tend to use their nuclear fuel more quickly. A planet around such a star may receive abundant energy, but the star's lifetime can be shorter, and its stronger ultraviolet output may alter or erode an atmosphere. The time available for biology may be measured differently there. Smaller stars burn their fuel far more slowly. Orange dwarfs, cooler and less massive than the Sun, are often considered appealing places to search. They can remain steady for much longer than Sun-like stars, while their habitable zones sit at distances where planets may avoid some of the harshest conditions found close to the smallest red dwarfs. Their light is warmer, in color their lives are extended, and they may offer long intervals during which a planet can settle into a stable climate. Red dwarfs carry the possibility even further. They are the most common stars in the Milky Way. They are faint, small, and so efficient with their fuel that the least massive among them can continue shining for timescales far beyond the current age of the universe. Around such a star, a planet may have more time than any world circling a Sun-like star could ever receive, but the useful starlight lies close to the source. A planet in the habitable zone of a red dwarf may complete an orbit in days or weeks, rather than a year. At that distance, the star's gravity can gradually synchronize the planet's rotation with its orbit. One hemisphere may remain turned toward the star, while the other faces away. It is easy to imagine this as a world divided into fire and ice, with no moderate place between them. The physics is more flexible than that. If the planet keeps a substantial atmosphere or ocean, winds and currents can carry heat toward the night side. Clouds may form over the illuminated hemisphere and reflect part of the incoming energy. A broad region of temperate conditions could exist near the boundary between day and night, or even across much of the globe. Tidal locking is not a sentence of sterility. It is a different climate problem. The greater concern may come from the star's youth. Young red dwarfs can remain magnetically active for long periods. They produce flares, ultraviolet radiation, and streams of energetic particles that can heat the upper atmosphere of a nearby planet and drive gases into space. Before settling into their long, restrained adulthood, some red dwarfs may spend hundreds of millions of years exposing close planets to conditions that make it difficult to retain water and air. A planet may survive that early stage if it begins with a large supply of volatiles, if its atmosphere is replenished by volcanic activity, or if much of its water remains protected in the interior. A magnetic field may help with some forms of particle exposure, though an atmosphere itself provides important protection. The result depends on the star, the planet, and the history they share. This is why red dwarf planets remain both promising and uncertain. Their stars are numerous. Their planets are easier for our instruments to detect because their orbits are short and the stars are small. Their lifetimes are immense, yet the same closeness that makes them observable also places them near the activity of their host stars. For observers on Earth, stars often appear permanent. Across many generations, people learned the repeated motions of bright points over the horizon. Stars became seasonal markers, directions over water, and measures of the night. Their apparent constancy offered a dependable pattern against the changing landscape below. On cosmic timescales, each of those lights has a history. Some stars spend long intervals in relative calm. Others pulse, flare, brighten, or age quickly. A world beneath one of them receives not a timeless beam, but a changing environment. The sky can shape the atmosphere, the ocean, and the chemistry below it long before anything living appears. There are more complicated skies as well. Many stars belong to pairs or larger systems. Planets can orbit one member of a pair or circle both stars at a greater distance. In those systems, the pattern of light may vary as the stars move around each other. The gravitational architecture must remain stable, and the planet's climate must respond to a changing energy supply. Yet such worlds are not ruled out. Planet formation can proceed in binary systems, and stable orbits can survive there. A sunrise beneath two stars would be visually unfamiliar, but the underlying requirement would remain the same. Energy must arrive in a range the world can use, and it must do so with enough continuity for chemistry to retain what it builds. The color of the light matters too. Cool stars produce a larger share of their energy at red and infrared wavelengths. Ice and snow absorb some of this light differently than they absorb the visible light of the sun, which can alter climate feedbacks. Any photosynthetic organisms would also meet a spectrum unlike the one that shaped Earth's plants. They might use different pigments or collect energy in different parts of the available light. None of this requires life to resemble vegetation under a red sky. It only reminds us that the star is not a lamp with a single brightness setting. It is a source of heat, radiation, particles, and time, all arriving together. When astronomers place a planet inside a habitable zone, they have identified the beginning of an investigation. They still need to know whether the world has air, whether it kept its water, whether clouds cool it or warm it, whether its orbit is stable, whether its star was calm enough during the planet's early history, whether the useful conditions lasted for 1,000,000 years, 1,000,000,000 years, or never existed at all. A promising distance can narrow the search. Only the history of the whole system can reveal whether that promise endured. A planet may receive the right amount of starlight and still fail to keep a place where life can begin. The atmosphere often decides what happens next. From a great distance, an atmosphere seems almost weightless. It may form only a thin shell around a rocky world, yet within that shell, pressure, temperature, wind, clouds, and chemistry can transform the same amount of incoming light into very different surface conditions. The clearest examples are close to home. Venus and Earth are similar in size. They formed in the same solar system from related materials. Both possess rocky surfaces, iron-rich interiors, and atmospheres shaped by volcanic activity. Yet their climates separated so completely that one became a world of oceans and temperate continents, while the other developed a surface hot enough to damage many metals. Venus receives more sunlight than Earth, but distance alone does not explain its present state. Its atmosphere is dominated by carbon dioxide and is far denser than Earth's. Sunlight reaches the cloud tops, and part of that energy enters the atmosphere below. The warmed surface releases infrared radiation, but the thick carbon dioxide envelope absorbs much of that outgoing heat and returns some of it downward. This is the greenhouse effect. a natural process rather than an error in planetary design. Without greenhouse gases, Earth would be far colder than it is now. Water vapor, carbon dioxide, methane, and other gases help keep the lower atmosphere warm enough for oceans to remain liquid across much of the planet. The problem is not the existence of a greenhouse effect. It is the strength of the effect and whether a world possesses processes that can regulate it. At some point in Venus's early history, warming may have caused surface water to evaporate more rapidly. Water vapor is also a powerful greenhouse gas. More vapor would have trapped more heat, leading to additional evaporation. If the process continued far enough, the oceans would have moved into the atmosphere. High above the surface, ultraviolet light could break water molecules apart. Hydrogen, being light, could escape into space. The heavier oxygen might react with rocks or be lost through other processes. Over time, a world that may once have held water could become dry, with carbon dioxide remaining as the dominant atmosphere. The exact history of Venus is still being reconstructed. Its surface has been altered by volcanic activity, and only a limited number of spacecraft have operated there. But its present condition shows that a rocky planet can occupy a region near the traditional habitable zone and still become hostile to surface life. Mars followed a different path. The planet is farther from the Sun, smaller than Earth, and now wrapped in an atmosphere so thin that surface pressure is less than 1% of sea level pressure on our world. Liquid water cannot remain exposed there for long. It tends to freeze, evaporate, or move directly between ice and vapor. Yet ancient valleys, layered sediments, deltas, and water-shaped minerals reveal that early Mars was not always like this. Rivers crossed its surface. Lakes filled impact basins. Water interacted with rock for long intervals. The atmosphere must once have been thicker, and the climate must have allowed at least temporary periods of liquid water. Mars gradually lost much of that protection. Its lower gravity made it easier for atmospheric particles to escape. Ultraviolet radiation split molecules in the upper atmosphere. Charged particles from the Sun interacted with gases and carried some of them into space. The planet's interior also cooled more rapidly than Earth's, reducing volcanic replenishment over time. Mars still has a magnetic field recorded in parts of its crust, evidence that an early internal dynamo once operated. That global field later faded. Without it, the upper atmosphere became more directly exposed to the solar wind. A magnetic field can help protect a planet, but its role is not as simple as a shield that guarantees survival. Venus lacks an Earth-like global field and still retains a very thick atmosphere. Some atmosphere can be lost, even when a magnetic field exists. Gravity, atmospheric composition, volcanic activity, stellar radiation, and the chemistry of the upper atmosphere all influence the final result. What Mars demonstrates is not that every habitable world must possess one particular defense. It demonstrates that atmospheres are temporary unless a planet can retain, recycle, or replace them. Earth does this in several ways. Its gravity is strong enough to hold a substantial atmosphere. Its interior remains active. Volcanoes release gases. Oceans absorb them. Rocks react with them. Life alters them. The atmosphere is part of a circulating system, rather than a fixed layer placed around the planet at formation. Carbon moves continually through this system. Some carbon dioxide dissolves in rainwater and forms a weak acid. The water reaches exposed rock, where chemical weathering releases dissolved materials. Rivers carry those materials toward the ocean. There, carbon can become incorporated into carbonate minerals and settle into sediments on the seafloor. This process removes carbon dioxide from the atmosphere over long timescales. If removal continued without interruption, the planet could eventually lose too much of its greenhouse warming. But Earth also returns carbon to the air. Oceanic crust and sediments descend into the mantle, at subduction zones. Heat and pressure alter the buried material. Carbon returns through volcanic gases and other forms of geological release. The full cycle unfolds over millions of years. Its pace is too slow to notice across a human lifetime, yet it helps regulate climate across ages. When conditions are warm and wet, chemical weathering can proceed more quickly, drawing down more carbon dioxide. When large regions become cold or ice-covered, weathering slows, allowing volcanic carbon dioxide to accumulate. This feedback does not prevent every climate extreme. Earth has passed through severe glaciations, warm greenhouse intervals, abrupt disruptions, and mass extinctions. But liquid water has remained somewhere on or beneath the surface for billions of years. That continuity may be more important for life than an unchanging climate. Living systems can adapt to shifting environments, but they need refuges. An ocean beneath ice, a warm region near the equator, a sheltered seafloor, or a network of groundwater can preserve biology while the surface changes. A planet does not need to remain comfortable everywhere. It needs to avoid becoming sterile everywhere at once. Plate tectonics may help Earth maintain this long exchange between atmosphere, ocean, and interior. Whether it is required for long-term habitability remains uncertain. Venus does not show Earth-like moving plates. Though it is volcanically active, Mars appears to have a rigid outer shell today. Some rocky exoplanets may recycle their crust through processes unlike those on Earth. Others may keep climate stable through ocean chemistry, localized volcanism, or atmospheric cycles we have not yet observed. This uncertainty matters because geology is difficult to measure from interstellar distances. A transit can reveal a planet's radius. The pull on a star can provide an estimate of mass. Together, these measurements suggest whether the world is rocky, rich in water, or surrounded by a deep gaseous envelope. Spectroscopy may reveal parts of the atmosphere, but plate movement leaves no simple signal in starlight. A distant observer might detect carbon dioxide and water vapor without knowing whether carbon's cycles through the crust. The planet might possess continents, global oceans, or a surface sealed beneath high-pressure ice. It might be geologically active beneath clouds that never separate. Habitability depends on processes hidden below the visible layer. The interior provides heat left from formation and from the decay of radioactive elements. That heat can melt rock, drive volcanism, power circulation in a metallic core, and maintain water beneath an icy crust. As a planet ages, its interior cools. The rate depends on its size, composition, structure, and history. Small worlds lose heat quickly because they have more surface area relative to their volume. Large rocky worlds can remain active longer, though greater pressure may also change how their interiors move. A super-Earth might sustain volcanism and a magnetic dynamo for a long time, or its mantle might behave in ways that make crustal recycling more difficult. There is no single planetary size that guarantees a living surface. Too little mass may make it difficult to hold air and internal heat. Too much mass may produce a deep atmosphere of hydrogen, or a thick layer of high-pressure ice separating an ocean from rock. Between these extremes lies a broad range of worlds whose behavior depends on details our current observations cannot yet resolve. Even Earth's atmosphere would be difficult to interpret from far away. Today, it contains nitrogen, oxygen, water vapor, carbon dioxide, and traces of many other gases. But this is not the atmosphere Earth began with. Free oxygen became abundant only after living organisms had already existed for a very long time. Early microbes transformed the air slowly. Photosynthetic organisms released oxygen, which first reacted with dissolved iron and surface materials. Only after many chemical sinks were filled did oxygen begin to accumulate more widely in the atmosphere. A distant observer looking at young Earth might have missed the presence of life. The planet could have shown methane, carbon dioxide, haze, and water vapor, while lacking the strong oxygen signal associated with its modern biosphere. It would have been inhabited but unfamiliar, suitable for organisms that did not need oxygen and dangerous to most complex life alive today. Habitability and human comfort are not the same condition. A world may support microbes in acidic clouds, beneath frozen soil, inside rock or near a seafloor vent. Its atmosphere may be toxic to us. Its surface pressure may be crushing. Its oceans may lie below kilometers of ice. Biology, if it begins, will respond to the environment that exists rather than waiting for one that resembles Earth. Still, an atmosphere offers several useful gifts. It provides pressure that helps keep water liquid. It redistributes heat through winds. It absorbs damaging wavelengths of radiation. It carries volatile compounds from place to place. It connects oceans, land, ice and rock through weather. It also records change. Gases released by volcanoes, removed by oceans, produced by sunlight, or altered by organisms can leave patterns that telescopes may eventually detect. The atmosphere is both part of the habitat and one of the few messages that a distant world can send. Yet that message is incomplete. A planet can look promising while hiding an unstable climate. It can look barren while sheltering water below. It can lose an atmosphere, rebuild part of it, freeze, thaw, and pass through several different states before life has enough time to begin. A living world is not defined by a perfect moment. It is defined by whether opportunity survives the changes that follow. Far beyond the reach of any spacecraft, a planet can still reveal itself through the light of its star. The planet may be too small and too dim to see directly. Its surface may reflect only a faint fraction of the light falling upon it. From Earth, star and planet often merge into a single point, with the brighter object overwhelming the darker one. Astronomers learn to work around that brightness. One method begins with gravity. A planet does not orbit a perfectly motionless star. Both bodies move around a shared center of mass. The star's motion is usually small, but it leaves a trace in the spectrum of its light. As the star moves slightly toward Earth, the wavelengths of its light compress. As it moves away, they stretch. Repeated shifts can reveal an unseen companion moving in a regular orbit. This radial velocity method provides information about the planet's mass and orbital period. Large planets close to their stars produce stronger signals. Small rocky planets in wider orbits produce movements so slight that stellar activity, instrument noise, and even patterns on the star's surface can become difficult to separate from the planet itself. Another method waits for a planet to cross in front of its star. During a transit, the planet blocks a small portion of the starlight. The size of the dimming reveals the planet's radius relative to the star. If the dip repeats at regular intervals, astronomers can calculate the length of the orbit. The alignment must be favorable. Most planetary systems are tilted, so their worlds never pass between their stars and Earth. A transit survey therefore misses many planets that certainly exist. Yet when the geometry is right, a transit can provide more than a count. Some of the starlight passes through the upper layers of the planet's atmosphere before reaching a telescope. Molecules absorb particular wavelengths, leaving narrow features in the spectrum. By comparing the star's light during and outside the transit, astronomers can search for the chemical fingerprints of water vapor, carbon dioxide, methane, and other gases. The measurement is delicate. Only a thin ring of atmosphere filters the light. Clouds and hazes can hide the layers below. The star itself may contain spots, bright regions, or flares that alter its spectrum during the observation. Several transits may need to be combined before a useful signal appears. Even then, a detected molecule does not explain how it formed. Water vapor may indicate an atmosphere capable of transporting moisture, but not necessarily an ocean. Carbon dioxide can be released by volcanoes, or locked into a dense atmosphere on a dry world. Methane can be produced by organisms, but it can also emerge from reactions between water and certain rocks. The search for life, therefore, depends less on finding one dramatic molecule than on recognizing a chemical pattern. On Earth, oxygen is continually produced by photosynthetic life. Without replenishment, much of it would react with rocks, volcanic gases, and reduced compounds. Methane is also removed by atmospheric chemistry and sunlight. Their coexistence can suggest an active source maintaining both gases. But nature can create misleading combinations. Ultraviolet radiation may break water molecules apart, allowing hydrogen to escape and oxygen to accumulate without life. Geological reactions may release methane. A planet with little surface water might build an oxygen-rich atmosphere through processes unrelated to biology. This is why scientists speak of biosignatures as evidence rather than proof. The atmosphere must be interpreted as a system. The planet's star, temperature, mass, surface conditions, geological activity, and atmospheric history all shape what the spectrum means. The same gas can carry different implications on different worlds. A convincing detection would likely involve several lines of evidence agreeing at once. There might be water vapor, together with gases that remain far from chemical equilibrium. Seasonal changes might appear. Surface colors could shift in ways consistent with pigments, though such a measurement would be difficult. Atmospheric compounds might occur in ratios that geological models struggle to reproduce. The strongest case would not come from a single feature. It would emerge gradually from a collection of measurement fins that leave fewer and fewer non-living explanations. This is slow work by design. When a distant planet is involved, certainty must be assembled from traces. A spectrum is cleaned of instrumental effects. Stellar behavior is modeled. Clouds are considered. Alternative chemical pathways are tested. Different research groups return to the same data with different assumptions. A promising result may become weaker after further analysis. An ambiguous signal may become clearer after several years. The movement from possibility toward confidence is rarely smooth. There is something fitting about this pace. For most of human history, the planets beyond the solar system were invisible. Their existence was inferred through reason long before it could be measured. Then the first confirmed detections showed that planetary systems were not unusual exceptions. They were widespread. Some contained giant planets orbiting close to their stars. Others held compact groups of rocky worlds. Some planets followed highly elongated paths. Some moved around pairs of stars. The first discoveries did not reveal copies of our solar system, arranged in familiar order. They revealed a large range of outcomes than the single system around the Sun had prepared us to expect. The variety changed the search for life. A habitable planet could no longer be imagined only as another Earth circling another sun. It might orbit an orange dwarf. It might belong to a tightly packed system. It might be larger than Earth while remaining rocky. It might be tidally locked. It might share its sky with another nearby planet, large enough to appear as a visible world rather than a point. Among the systems found so far, some have become natural laboratories. TRAPPIST-1 is a small red star surrounded by 7 known planets close to Earth in size. Their orbits fit inside a region much smaller than the orbit of Mercury, yet the star is faint enough that several receive amounts of energy that place them near the range associated with possible surface water. The planets are linked through orbital resonances. Their gravitational pulls affect one another, causing small variations in transit timing. Those variations help astronomers estimate their masses and densities. The system offers several rocky worlds formed around the same star. They can be studied as a family. If one retained an atmosphere while another lost its gases, the difference could reveal how orbital distance, radiation, and planetary mass shaped their histories. If several are airless, the result would place limits on the ability of close red dwarf planets to preserve atmospheres. If one holds water vapor or carbon dioxide, the finding would show that survival is possible under at least some conditions. The nearest known planet in a temperate orbit presents another kind of opportunity. Proxima Centauri b circles the closest star to the Sun. Its presence was detected through the motion it induces in the star. It receives an amount of stellar energy that places it within the broad range where liquid water might be possible. But the planet does not transit from our viewpoint, so its radius and atmosphere remain difficult to measure. Proxima Centauri is also an active red dwarf. Flares and high-energy radiation may have shaped the planet's surface and atmosphere for billions of years. The nearness of the system does not make the answer simple. It does make the question feel less abstract. A potentially temperate rocky planet does not exist only in a distant region of the galaxy. One circles the star next door. Whether it is dry, frozen, airless, ocean-covered, or chemically active remains unknown, but its existence confirms that small planets in temperate orbits are not confined to remote parts of the Milky Way. Other candidates orbit farther away, known mostly through their size, mass, and distance from their stars. Some circle Sun-like stars. Others orbit cooler orange dwarfs or red dwarfs. Many are too distant for detailed atmospheric study with current instruments. A planet can be added to a catalogue long before its true nature becomes clear. The word candidate carries this uncertainty. A world may look favourable because of its radius and orbit, while its atmosphere remains hidden. It may turn out to be a dense mini-Neptune with a deep hydrogen envelope rather than a rocky surface. It may possess high-pressure layers of ice beneath an ocean, preventing contact between water and the minerals below. It may be cloud-covered, dry, or geologically inactive. The catalogue is a map of places worth examining, not a census of living worlds. Direct imaging offers another path. Instead of waiting for a transit, a telescope can attempt to separate the light of the planet from the glare of the star. A coronagraph blocks part of the starlight inside the instrument. A starshade proposed for some future missions would fly far from the telescope and cast a carefully shaped shadow, allowing nearby planets to appear beside their stars. The challenge resembles seeing a pale speck close to a brilliant beacon, but direct imaging carries an advantage. It can study planets whose orbits never produce transits. It can observe a world at different positions in its year. It may eventually reveal clouds, atmospheric changes, rotation, and reflected light spectra. Future observatories are being designed with this purpose in mind. Their goal is not only to discover more planets, but to examine nearby rocky worlds around relatively stable stars. The most useful targets will likely be close enough for repeated observations and separated far enough from their stars to reduce the problem of glare. Each improvement in telescope design expands the range of questions. A larger mirror gathers more light. Better detectors measure weaker signals. Improved control of starlight makes smaller planets visible. Longer observation times reveal slower orbits and subtler atmospheric features. The instruments may eventually identify a planet whose spectrum resembles no lifeless world in our models. Even then, the first interpretation will be cautious. Researchers will ask whether the star could have produced the signal. They will examine volcanic chemistry, atmospheric escape, ocean reactions, and unusual mineral pathways. They will look for observational errors and independent confirmation. A claim about life beyond Earth must survive every reasonable alternative. This restraint does not diminish the discovery, it protects it. For now, the telescopes are gathering fragments: a radius, a mass, a repeating shadow, a faint atmospheric absorption line. None alone can reveal an inhabited world. Together they are beginning to turn distant points into places. The light arrives carrying the history of air it crossed, And for the first time, we have instruments patient enough to read it. The search becomes wider. Once sunlight is no longer treated as the only useful source of energy. Far from the sun, beyond the orbit of Mars, and deep within the colder regions of the solar system, several moons appear frozen from the outside. Their surfaces are bright, rigid, and marked by fractures. Temperatures are far below the freezing point of water. No rain falls there. No open ocean reflects the sky, and yet beneath the ice, water may move. Europa, one of the large moons of Jupiter, is one of the clearest examples. Its surface is made mostly of water ice, crossed by long lines, ridges, and disrupted regions where the crust appears to have shifted and refrozen. The surface is young by planetary standards. There are fewer large impact craters than would be expected on an ancient unchanged age world. Something has repeatedly altered the ice. The source of that activity lies in Europa's orbit. Europa does not move around Jupiter in a perfect circle. Its path is slightly elongated, maintained in part by gravitational interactions with neighboring moons. As Europa travels closer to and farther from Jupiter, the strength of the planet's pull changes. The moon is flexed. Its interior stretches and relaxes with each orbit. Rock and ice deform under the repeated stress, and friction converts some of that movement into heat. This process, known as tidal heating, supplies energy in a region where sunlight alone would never keep a large body of water liquid. Beneath the outer shell, evidence points toward a global ocean. That ocean may contain more water than all of Earth's surface oceans combined. The exact thickness of the ice and depth of the water remain uncertain, but the important boundary lies at the bottom, where the ocean may meet a rocky seafloor. Water in contact with rock creates chemical possibilities. On Earth, seawater moves into cracks in the ocean crust. It becomes heated, reacts with minerals, and rises again carrying dissolved compounds. Around hydrothermal vents, these reactions create strong chemical gradients. Microorganisms use those gradients as sources of energy. Europa may possess some version of this process. Its rocky interior may still release heat. Water may circulate through fractures. Minerals may dissolve and return to the ocean. If the chemistry is suitable, the seafloor could provide energy for biology without any light reaching the water above. The ice would create both an obstacle and a refuge. It separates the ocean from sunlight and makes direct observation difficult. At the same time, it protects the water from radiation surrounding Jupiter. Europa's surface is exposed to a harsh environment of energetic particles trapped within the planet's magnetic field. A deep ocean below kilometers of ice would be shielded from much of that radiation. But the outer shell may not be completely sealed. Some surface features suggest that material from below has reached upward, while surface compounds may be carried downward through fractures or slow recycling of the crust. If that exchange occurs, oxidants produced near the surface could enter the ocean and provide additional chemical energy. The question is not only whether Europa has water, it is whether the water, rock, and chemistry remain connected. A completely isolated ocean with little chemical variation might offer fewer pathways for metabolism. An ocean with active circulation, mineral reactions, and exchange through the ice would be more dynamic. The difference cannot be seen from the appearance of the moon alone. Another moon, much smaller and farther away, makes the hidden ocean easier to reach. Enceladus circles Saturn. Its surface is covered in clean, reflective ice. Near the South Pole, long fractures cut across the terrain. From those openings, jets of water vapor and ice grains rise into space. The ocean below does not remain entirely hidden. Material from the interior escapes through the cracks, creating a plume that can be sampled by a passing spacecraft. This gives Enceladus a rare scientific advantage. Studying its ocean does not necessarily require drilling through the crust. The moon brings part of the ocean outward. Measurements of the plume have revealed water salts, organic compounds, silica particles, and molecular hydrogen. Each clue speaks to conditions beneath the ice. Salts suggest that the water interacts with rock. Silica particles point toward warm water reactions at the sea floor. Molecular hydrogen can be produced when water reacts with certain minerals in a process that releases chemical energy. On Earth, microbes can use hydrogen as part of their metabolism. They combine it with carbon dioxide and produce methane, gaining energy from the reaction. The presence of hydrogen on Enceladus does not mean that organisms are using it. It means that a usable source of chemical energy appears to exist. This distinction remains central to the search. A place can contain the ingredients of life without containing life. Water, organic molecules, and energy may remain separate or interact in ways that never lead to self-replication. Still, Enceladus brings many favorable conditions together in a small world. Liquid water is present. The ocean meets rock. Chemical energy is available. Organic compounds exist. The ice protects the interior. Material circulates from the ocean into space. A moon that appears frozen and inactive from a distance turns out to be exchanging matter continuously between its interior and its surroundings. The lesson extends beyond Europa and Enceladus. Ganymede, the largest moon in the solar system, is believed to contain layers of water beneath its surface. Callisto may also hold a buried ocean. Titan, Saturn's largest moon, has lakes and seas of liquid hydrocarbons on its surface and likely a water-rich ocean far below. Even distant bodies such as Pluto show signs that their interiors may have retained more heat than their size and distance would suggest. The outer solar system may contain many more liquid environments than the sunlight at those distances seems capable of supporting. Some oceans are maintained by tides. Others may be kept warm partly by radioactive decay within rock. Heat left from formation can also remain trapped beneath insulating layers. Ice is effective insulation. A thick shell slows the escape of internal heat. Once an ocean forms beneath it, the overlying ice can help preserve liquid water over immense periods. The surface may fall to extremely low temperatures, while conditions below remain comparatively stable. This introduces a different kind of habitable zone. Instead of a ring around a star, the useful region exists inside a world. Its boundaries are set by ice thickness, internal heat, pressure, chemistry, and the contact between water and rock. The star may influence the environment only indirectly. A moon can therefore remain chemically active far beyond the classical habitable zone. A planet without a star might also preserve hidden water. During the formation of planetary systems, gravitational encounters can eject worlds into interstellar space. These rogue planets travel through the galaxy without orbiting a sun. Their surfaces would receive almost no starlight, and any exposed ocean would freeze. But complete freezing is not guaranteed. A sufficiently thick layer of ice could insulate water below. Radioactive elements in the rocky interior would continue releasing heat. If the planet retained a dense atmosphere or formed with a large internal energy supply, liquid regions might persist for long periods. Such a world would have no sunrise. Its surface would remain dark except for distant stars and the faint background of the galaxy. Beneath the ice, however, water could circulate slowly around a warm interior. Whether life could begin there is deeply uncertain. The chemistry of origin may require ultraviolet light, wet and dry cycles, surface minerals, or repeated changes that are difficult to produce in a sealed ocean. It may also be possible for hydrothermal systems alone to provide the necessary pathways. At present, both possibilities remain open. This difference between origin and survival becomes more important with every hidden ocean. An environment may be excellent at protecting organisms once they exist, but poor at creating the first ones. A thick ice shell shields an ocean from radiation and climate disruption, yet it also prevents evaporation, drying, and exposure to sunlight. If early life needs alternating conditions, then a completely covered ocean could be too uniform. But an ocean world may contain its own cycles. Water can circulate between warmer and colder regions. Minerals can dissolve and precipitate. Pores in rock can create microscopic compartments. Ice at the base of the shell can melt and refreeze. Pressure changes can open and close fractures. The relevant variation may occur without ever reaching the surface. On Earth, some of the oldest chemical systems are hidden from view. Microbes live deep within rock, far below sunlight, using hydrogen, sulfur, iron, and carbon compounds produced through geological reactions. They reproduce slowly. Some survive with very little available energy. Their existence shows that biology can persist in places once assumed to be too isolated or inactive. The deep biosphere of Earth changes the scale of the question. The visible surface is only one layer of a living planet. Beneath oceans and continents, water moves through cracks and pores. Chemical reactions continue in the crust. Organisms inhabit spaces that never experience weather or daylight. If similar environments exist on other worlds, telescopes may have difficulty detecting them. A surface biosphere can alter an atmosphere. Plants, microbes, and oceans can release gases that accumulate above the ground. Those gases may leave spectral features visible across interstellar distances. A buried biosphere may send almost no message. Life beneath tens of kilometers of ice could remain separated from the atmosphere or from space. Its gases might dissolve in the ocean, react with minerals, or remain trapped beneath the crust. From Earth, the world might appear frozen and unremarkable. This creates a limit no improvement in telescope sensitivity can completely remove. Some habitable places may be hidden not because they are distant, but because they are enclosed. They could be common and still absent from our planetary catalogues. A system might contain several such environments without any obvious surface sign. Large planets could host families of icy moons. Rogue worlds could carry oceans through interstellar space. Cold dwarf planets could remain active beneath their crusts. The number of environments where life could persist may therefore be larger than the number we can count, and the places easiest to observe may not be the places most likely to preserve life. A warm surface planet offers atmospheric access, but also faces impacts, climate shifts, radiation, and atmospheric loss. A buried ocean is difficult to study, yet it may remain stable through changes that would erase life above. One environment is open to the sky, the other is protected from it. Neither can yet be called the better birthplace. They represent different solutions to the same requirement, keeping water, chemistry, and energy together long enough for matter to begin remembering what it has made. The next uncertainty begins after a world has gathered water, energy, carbon, and time. Those conditions can make chemistry active. They do not tell us when chemistry becomes alive. On Earth, life appeared early enough that the exact transition has been almost completely erased. The planet formed about 4.5 billion years ago. As its surface cooled, oceans formed, impacts continued, and the crust was repeatedly altered. By the time the oldest widely accepted evidence of life enters the record, the earliest chemical steps had passed beyond reach. We see the descendants, not the beginning. Every organism alive today belongs to a lineage that has been evolving for billions of years. Even the simplest modern microbe carries membranes, enzymes, genetic machinery, and systems for gathering energy. It is the result of a very long history. To understand where life could begin beyond Earth, scientists must work backward from this complexity. One possibility is that information came first. In modern cells, DNA stores genetic instructions, while proteins perform much of the chemical work. But DNA depends on proteins to be copied, and proteins depend on information encoded in DNA. Neither side can easily appear in its modern form without the other. RNA offers a possible bridge. Like DNA, RNA can store information in sequences of chemical units. Unlike DNA, some RNA molecules can also fold into shapes that speed up reactions. In principle, one molecule could have carried instructions while helping copy or modify other molecules. This idea is often called the RNA world hypothesis. It does not mean that a complete RNA-based organism appeared all at once. More likely, networks of simpler molecules formed, broke apart, and sometimes produced copies with small variations. Some sequences may have lasted longer or copied more efficiently. At that point, chemistry would begin to acquire a kind of memory. A successful arrangement would no longer vanish completely when its individual parts were replaced. Information could persist through copies. Variation could enter the process. Selection could favor structures that survived or reproduced more effectively. That movement from temporary reaction to inherited pattern may be one of the deepest thresholds in nature, but RNA itself is chemically demanding. Its building blocks must form. They must become concentrated. They must join in useful sequences. The surrounding environment must support those steps without destroying the products too quickly. This is why the setting matters as much as the molecule. Some researchers study shallow pools on young rocky worlds. Water could collect, evaporate, and return. Each drying cycle would concentrate dissolved compounds and bring them into closer contact. Sunlight and heat could drive reactions. Rain or tides could redistribute the products before another cycle began. Others examine mineral surfaces. Certain clays and metal-rich rocks can hold organic molecules in ordered positions. A surface may act like a temporary scaffold, making it easier for small units to connect. Minerals can also provide metals that help reactions proceed. Another family of ideas turns toward hydrothermal systems. At alkaline vents on the seafloor, warm fluid from within the crust meets colder ocean water. The vent structures contain tiny pores separated by thin mineral walls. Across those walls, differences in acidity and electrical charge can arise. Modern cells use comparable gradients across membranes to store and release energy. The resemblance is not proof that life began there. It shows that geology can create some of the same physical conditions biology later learned to control. The first living system may have emerged where several environments met. A shoreline might provide wet and dry cycles. Volcanic rock might supply reactive minerals. Ultraviolet light might build some molecules while damaging others. Groundwater could carry products into protected pores. There may never have been one perfect location. Instead, a young planet may have functioned as a network of chemical workshops. Materials formed in one place, traveled, changed in another, and accumulated somewhere else. The origin of life could have depended on movement between environments rather than residence within a single one. This possibility complicates ocean worlds. A buried sea may contain water, minerals, and energy for billions of years. It may be an excellent refuge once organisms exist. Yet if the first living chemistry needs drying, sunlight, or exchange with an atmosphere, a sealed ocean could face a harder beginning. That does not make it lifeless. Its seafloor may contain porous rock, temperature gradients, and cycles of freezing and melting near the base of the ice. Impacts early in its history may have created temporary openings. Material could have moved between surface and interior before the crust thickened, or life could arrive rather than begin there. Rocks are exchanged between planets and moons during large impacts. Material blasted from a surface can travel through space and fall onto another world. Meteorites from Mars have been found on Earth, proving that natural transfer occurs. Whether living organisms could survive ejection, radiation, long travel, and arrival is uncertain. Some microbes and spores can endure severe conditions for limited periods, especially when shielded inside rock. This has led to the idea of lithopanspermia, the transfer of life between neighboring worlds within a planetary system. Panspermia does not explain how life first began. It only moves life from one place to another. But if biology arose once in a system, impacts might spread it to several suitable environments. Mars and Earth may have exchanged material during their early histories. The distinction between origin and distribution matters when we count inhabited worlds. Several living places in one system might represent independent beginnings, or they might belong to one family, connected by ancient transfers of rock and ice. Only chemistry could reveal the difference. Life that began separately might use unfamiliar molecules, a different genetic code, or another method of building membrane. Life related to Earth would be expected to share deeper biochemical patterns even after billions of years of separate evolution. Finding a second genesis would change the meaning of habitability. If life arose independently on Mars, Europa, Enceladus, or another nearby world, then the transition from chemistry to biology would have happened at least twice within one small planetary system. That would suggest that life begins readily when conditions permit. If every nearby environment is sterile, the conclusion would be less direct. It might mean life is rare. It might mean we searched the wrong places. It might mean the evidence is buried beyond reach, or that living systems appeared and vanished long ago. Absence is difficult to establish on an entire world. Earth itself shows why. Life can persist in microscopic fractures, deep sediments, salt crystals, ice, acidic water, and hot rock. A mission could examine many sites and still miss a sparse biosphere. A sample might contain no cells even when organisms live a few meters away. The first confirmed discovery may therefore be subtle. It could be an unusual pattern of carbon isotopes in rock, a set of organic molecules with a strong preference for one orientation, repeated structures in a plume particle, or a chemical imbalance that geology cannot easily maintain. Each clue would require context. Life does not leave one universal mark. It alters the materials available to it. On one world, biology might change an atmosphere. On another, it might modify minerals at the bottom of an ocean. On a third, it might remain confined to pores in rock and never affect the surface. There is also no reason to assume that the first life becomes complex. For most of Earth's history, living things were microscopic. Simple cells transformed oceans and air long before animals appeared. Multicellular organisms required new forms of cooperation, communication, energy use, and genetic control. Intelligence came much later, and only one species on Earth has built instruments capable of searching other stars. This means several separate questions are often compressed into one. Can chemistry become life? Can simple life persist? Can it become complex? Can complex life develop technology? The conditions that help one step may not help the next. A stable ocean beneath ice could preserve microbes for billions of years, while offering little environmental variety for large organisms. A changing surface world could drive evolution through shifting habitats, but also expose life to repeated extinctions. There may be many inhabited worlds, and very few that ever become visible across interstellar space. For generations, people looked upward without knowing that planets circle most of the stars they saw. Those observers shared the same basic chemistry with every living thing around them. Yet the origin of that chemistry remained hidden beneath the age of the planet. Now, the question has moved outward, not because Earth's beginning has been solved, but because the galaxy provides other places where nature may have attempted the same transition. Some attempts may have stopped with organic molecules. Some may have reached self-replication and failed. Some may have produced microbial oceans that still continue beneath ice. And somewhere, on a world whose name we do not know, chemistry may have crossed the threshold and begun to remember itself. Once life becomes possible, the numbers begin to separate into questions that no telescope can answer all at once. How many stars have planets? How many of those planets can hold liquid water? How many remain suitable for long intervals? How often does chemistry become biology? And after life begins, how often does it grow complex enough to leave a signal that another world could notice? These questions may sound like stages in a single calculation, but each belongs to a different field of science. Astronomy can count stars and planets. Planetary science can model atmospheres and interiors. Chemistry can explore pathways towards self-replication. Biology can show what living systems are capable of becoming. Only one world currently connects all of those stages. Earth is therefore both our best guide and our greatest limitation. In 1961, astronomer Frank Drake arranged the uncertainty into a sequence that became known as the Drake equation. It was not intended to function like a physical law. It was a way to divide one immense question into smaller parts. The equation begins with the formation of stars. It asks what fraction of stars possess planets, how many of those systems contain environments suitable for life, how frequently life appears, how often intelligence develops, and how long a technological civilization remains detectable. When the equation was introduced, even the early astronomical factors were poorly known. Planets beyond the solar system had not yet been confirmed around ordinary stars. Astronomers could debate whether planetary systems were common, but they could not settle the question through observation. That part has changed. Planet formation appears to accompany star formation across much of the galaxy. Surveys have revealed worlds around stars of many sizes and ages. Some systems contain gas giants, some contain rocky planets, and many contain arrangements unlike the one surrounding the Sun. The first steps in Drake's sequence have moved from speculation toward measurement. The later steps remain open. No observation has yet revealed how frequently life begins on a suitable world. No survey can tell us how often microbial life develops multicellular bodies, nervous systems, intelligence, or technology. We do not know how long technological societies tend to remain detectable, or whether detection is a stage most civilizations would pass through at all. A civilization might use radio communication for only a brief part of its history. It might direct signals narrowly, rather than broadcast them in every direction. Its technology might produce signatures we have not learned to recognize. Even two civilizations existing in the same galaxy could miss each other in time. One might flourish for 10,000 years and disappear millions of years before another begins listening. Their planets could both be inhabited, both capable of communication, and still remain separated by chronology rather than distance. The Milky Way has had billions of years in which such intervals could occur. This makes a present-day count different from a count of every civilization that has ever existed. A galaxy may have produced many technological species while containing very few at the same moment. Distance adds another delay. A radio message crossing 100 light-years carries information from 1 century in the past. A response would need another century to return. Across greater distances, communication becomes an exchange between generations. The sky we observe is not a picture of the galaxy as it is. Now, it is a layered record of earlier moments. Light from nearby stars may be only a few years old. Light from distant regions of the Milky Way began traveling before many human cultures took their present forms. When we search for signs of technology, we search through this uneven history. The modern search for extraterrestrial intelligence often looks for technosignatures. A technosignature is any observable feature that might be produced by technology rather than by ordinary natural processes. A narrow radio signal is one possibility. Brief pulses of light, unusual atmospheric compounds, large-scale energy use, or patterns of heat might offer others. Radio remains useful because it can cross interstellar space, and because natural radio sources tend to spread their energy across predictable ranges. A signal concentrated into a very narrow frequency can stand out, but the number of possible frequencies is enormous. A search must choose a region of the sky, a group of stars, a band of frequencies, a sensitivity level, and a period of observation. A signal may occur outside that band. It may be too weak. It may arrive when the telescope is pointed elsewhere. It may repeat only after years. Searching a star once is not the same as knowing that no signal comes from it. The situation is sometimes compared to sampling a small amount of water from an ocean and finding no fish. The sample contains information, but its emptiness cannot describe the entire sea. This is why the absence of a confirmed technosignature does not yet establish that the galaxy contains no technological life. It tells us that no signal has survived the full process of detection, verification, repetition, and independent confirmation. That standard must remain high. Radio telescopes regularly receive interference from satellites, aircraft, ground transmitters, and electronic equipment. Natural objects also create signals that can initially appear unusual. A candidate must be checked against its movement across the sky, its frequency behavior, its timing, and the possibility of human contamination. A real discovery would need to appear again. It would need to remain associated with a location beyond Earth. Other observatories would need to detect it. Its structure would have to resist natural and technological explanations close to home. Most interesting candidates fade during this process. That is not failure. It is how the search becomes trustworthy. The same care applies to atmospheric signs of biology. A gas that seems biologically suggestive may also come from volcanoes, sunlight, or water interacting with rock. A planet must be understood as a whole before one chemical feature can carry much weight. Life and technology both need context. The unresolved distance between large estimates of habitable environments and the lack of confirmed evidence for civilizations is often called the Fermi paradox. Its central idea is simple. If suitable worlds are numerous, and if some civilizations become capable of spreading signals or machines between stars, why have no unmistakable signs appeared? The question is useful because it exposes the assumptions hidden inside it. Perhaps the origin of life is rare, even when planets are suitable. Perhaps microbial life is common, while complex life seldom develops. Perhaps intelligence appears in many forms, but rarely produces technology that can be observed from another star. Perhaps interstellar expansion is more difficult, less desirable, or less enduring than simple calculations assume. Perhaps technological societies communicate in ways that leave little trace at our present level of understanding. There is also the possibility that the galaxy contains evidence we have not searched widely enough to find. Our period of systematic listening is brief beside the age of the Milky Way. Our instruments cover only parts of the sky and only parts of the possible signal space. The work has begun, but the scale of the task remains much larger than the portion completed. The Fermi paradox is therefore not proof of absence. It is a mismatch between what some estimates appear to allow and what observations have so far confirmed. That mismatch could be resolved in many ways. A future telescope might find that atmospheres on temperate, rocky planets are uncommon, narrowing the number of stable surface environments. A mission to an icy moon might discover biological chemistry, showing that simple life can begin in places hidden from starlight. A confirmed biosignature on even one exoplanet would change the early biological factors in every estimate. A second independent example of life within the solar system would change them more directly. Two origins in one planetary system would suggest that biology may emerge readily under suitable conditions. On the other hand, decades of careful observations may reveal many promising environments without finding a sign of life. That outcome would not prove that everyone is empty, but it would begin to place limits on how easily biology appears or becomes detectable. The uncertainty will narrow through accumulation rather than through one perfect measurement. A spectrum here, a plume sample there, a planetary atmosphere that can be ruled out, a chemical pattern that remains unexplained. Across generations, these fragments may become a statistical picture of life in the galaxy. The observers who began searching by radio in the 20th century knew of no confirmed planets beyond the solar system. Later astronomers inherited their question and gained thousands of worlds on which to test it. Future observers may inherit atmospheric maps, direct images, and samples from buried oceans. Each generation receives a larger universe than the one before it. For now, Earth remains the only world known to have crossed every threshold, from chemistry to cells, from cells to complex organisms, and from organisms to instruments that can examine distant planets. That sequence may be common, it may be rare, or different worlds may follow paths so unfamiliar that our sequence is only one branch among many. The galaxy has not yet given us a clear answer. It has given us enough worlds to make the question unavoidable. There is no final number waiting at the end of this search. Not yet. Astronomers can estimate how many rocky planets occupy temperate orbits. They can model how many may keep atmospheres, oceans, or active interiors. They can examine distant air and material rising from hidden seas. But the step from a suitable environment to a living one remains beyond any complete calculation. The next answers will come from several directions at once. The James Webb Space Telescope is already measuring the atmospheres and temperatures of small planets around nearby stars. Some appear to have little or no atmosphere. Others remain difficult to interpret because clouds, stellar activity, and weak signals leave several possibilities open. For many years, a rocky exoplanet was known mainly by its size, mass, and orbit. Now some can be studied as physical environments. Their daysides can be compared with climate models. Their spectra can be tested for gases. The question is shifting from whether a planet exists to what kind of place it may be. The first results will not all point toward habitability. Learning that a world is airless is useful. Finding that close planets around an active red dwarf have lost their atmospheres would place limits on one of the galaxy's most common planetary settings. Finding that another has retained air would show that survival depends on details rather than one rule. Negative results narrow the map. Ambiguous results reveal which instruments must come next. On a mountain in Chile, a new generation of ground-based observation is taking shape. The extremely large telescope is being built around a primary mirror 39 meters across. When scientific observations begin, its collecting area and fine resolution will allow astronomers to study nearby planetary systems with greater sensitivity than present ground-based instruments. It may help separate the faint reflected light of planets from their stars. It may measure atmospheric gases, planetary motion, and the environments around young worlds. It will not answer every question alone, but it will add another form of evidence. Farther ahead, the Habitable Worlds Observatory is being developed as a future space telescope designed around a direct goal: finding and studying potentially Earth-like planets around stars more similar to the Sun. The challenge is contrast. A small rocky planet is billions of times fainter than the star beside it in visible light. To study such a world directly, a telescope must suppress the starlight with remarkable precision while preserving the much weaker planetary signal. If that can be done across enough nearby systems, astronomers could collect reflected light spectra from worlds that do not transit their stars. They could search for water, oxygen, carbon dioxide, methane clouds, and other signs of atmospheric activity. No single gas would settle the question. The strength would come from context, the star's spectrum, the planet's orbit, the atmospheric mixture, the climate, and whether the observed chemistry can remain stable without continual replenishment. a convincing biosignature may first appear as a pattern that refuses to fit a lifeless model. It may take years of repeated observations before the pattern becomes clear. Different telescopes may examine the same planet at different wavelengths. Models will be revised. Alternative explanations will be tested. The discovery, if it comes, may grow slowly from agreement among many measurements. Closer to home, another search is traveling outward through the solar system. Europa Clipper is on its journey to Jupiter, where it is scheduled to arrive in 2030. The spacecraft will not land on Europa or drill through the ice. Instead, it will make repeated close flybys using radar, cameras, magnetic measurements, and chemical instruments to study the Moon's shell, ocean, surface, and surrounding environment. Its purpose is to ask whether Europa contains places that could support life. That wording matters. A mission can investigate habitability without claiming to detect organisms. It can measure the structure of ice, look for pathways between the surface and ocean, examine salts and organic compounds, and estimate whether water meets rock below. These results could transform Europa from a promising idea into a more precisely understood environment. Enceladus may one day receive an even more direct investigation. Its plume carries ocean material into space, where a spacecraft could search for complex organic patterns, chemical imbalances, or structures that would be difficult to explain through geology alone. Mars continues to hold another kind of record. Its sediments preserve a time when rivers and lakes existed on the surface. Samples from carefully chosen ancient rocks could reveal whether organic compounds were produced by biology, altered by radiation, or formed through non-living chemistry. Venus, Titan, and other worlds add different possibilities. Each carries a separate combination of solvent, energy, atmosphere, and geology. None should be treated as a hidden Earth. Their value lies in showing how many physical paths a planetary environment can follow. The search may eventually find that life favors only a narrow set of conditions. It may require liquid water touching rock, repeated chemical cycles, a stable climate, and a long interval of protection. It may begin easily once those conditions gather, or it may depend on a rare sequence that most suitable worlds never complete. There is no honest way to choose among these possibilities yet, but the uncertainty is becoming measurable. A generation ago, the existence of planets around other sun-like stars had only begun to move from speculation into observation. Today, thousands of worlds are known, and planetary systems are understood as a normal result of star formation. The next transition will be from counting planets to comparing environments. After that may come the first reliable statistics of atmospheres on rocky worlds. Then perhaps a biosignature, perhaps a sample from another ocean, perhaps an ancient chemical trace preserved in stone. Each result will change the meaning of the results that came before it. If life is found in a plume from an icy moon, worlds beyond stellar habitable zones will become central to the census. If a distant atmosphere contains a strong biological pattern, the galaxy will no longer be known from one living example. If many apparently suitable worlds remain barren, the origin of life will appear more selective. The universe does not owe us a simple answer. Life may be common in one form and rare in another. Microbial ecosystems could fill buried oceans, while technological species remain widely separated. Some worlds may live briefly and lose their air. Others may preserve small biospheres beneath ice for longer than stars like the Sun remain on the main sequence. The first discovery beyond Earth may answer one question while opening several more. It may show that biology exists elsewhere without revealing how it began. It may reveal unfamiliar chemistry without telling us whether complex life can follow. It may confirm a second inhabited world while leaving the greater galaxy uncertain. Still, one confirmed example would remove a boundary that has surrounded every human observation until now. Earth would remain our home, but it would no longer be the only known place where matter became living. Until that moment, the search continues through instruments, samples, equations, and patient doubt. Above the atmosphere, light from other worlds keeps arriving. Beneath distant ice, oceans may continue moving against rock. Around small stars, planets complete their close orbits under skies no human eye has seen. Some of those places may be empty, some may be waiting within chemistry's long unfinished process, and some may already contain the answer, held in water, air, or stone, beyond the reach of present tools. For now, the possible worlds remain beneath their distant light.